Previous classes we have studied about the different types of the microwave tubes and how these particular microwave tubes generate the oscillations and how the microwave tubes can be used for the amplification purposes. Now in the today's class, so let us consider the transmission lines. So the transmission lines are the medias through which an electrical energy will be transmitted from one point to the other point or from one place to the other place. Okay. Now, so these transmission lines in terms of communication systems if you consider, so the transmission lines are used to send the signals from transmitter to the antenna and at the transmitter side and from the antenna to the receiver at the receiving end. The transmission lines can be classified into two types. One is balanced transmission lines, another one is the unbalanced transmission lines. Okay. So in the balanced transmission lines, they are the one where we have two wires and they are parallel to each other. Okay. And the equal amount of the current flowing through these two particular lines, but whatever the voltage and currents are there which is passing through these particular lines, so they are out of phase with respect to each other. That is, we have two types of the transmission lines. One is balanced transmission lines, another one is unbalanced transmission lines. In the balanced transmission lines, a pair of conducting wires are there and this pair of conducting wires are separated by a distance and always they are parallel to each other and current flows through these two pair of wires and equal amount of the current is flowing through these particular wires and the voltage and the voltage and the current which are flowing through these particular wires, they are out of phase with each other. Whereas coming to the unbalanced transmission lines, the conducting wire is there. I mean to say that some of the examples of these unbalanced transmission lines are coaxial cables and your waveguides. Okay. In the coaxial cables, we are having the center conductors, then an insulating materials is there, so once again conducting materials are there, insulating materials are there. Okay. So these coaxial cables comes under the transmission lines. And in most of the communication systems, okay, we are preferring, so this unbalanced transmission lines, that is the coaxial cables and waveguides to send the signals from your transmitter to the antenna and to receive a signal from antenna to the receiver circuit. Okay. And in the microwave communications are considered, so generally we are coming across one particular term, that is a wave. Okay. Now first, before going to in detail of how these particular waves are transmitted and the waves are received, now let us consider what is meant by these waves. Okay. Now wave is nothing but a disturbance caused at a particular point at a particular instant of the time. And these these disturbances may occur at another instant at another place. That means to say that the wave are the nothing but the disturbances caused at one particular place at one particular time, and this disturbance may be occurring at some other place at some other instant of the time. When it is occurring at one place and then it is occurring at another place, then you are occurring at another place at the different instant of the time. So then this one we are calling it as a wave motions. Now let us consider this particular diagram regarding what I have told so far. Now, so let us consider here at the time instant t1, okay, at the time instant t1, one particular disturbance has been created. So this amplitude of this particular disturbance I am represented as this one. Okay. And so this particular disturbance is calculated at a distance x1 from the origin. Generally, in any case, we are considering the origin here. At a time instant t1, at this particular place, a disturbance has been at a distance x1, a disturbance has been calculated. Then once again a disturbance has been calculated at a distance of x2 and at a time instant of t2, and one more disturbance is calculated at a distance at a place or at a distance x3 and at a time instant of t3. Okay. Now this particular figure illustrates the wave motion, how the waves are moving. Okay. Now because wave is created here and wave will move to this particular place, and then this place, and then this particular place, and so on. So these things are moving, that is the disturbances are go on moving. This disturbance, what it is moving, so then we are calling it as in wave motions. Now, so whenever the wave is moving, so then it is moving with a certain speed or the speed, so then we are supposed to calculate the velocity. So velocity of this movement will be calculated from, so the x2 minus x1 divided by t2 minus t1, that is the x2 minus x1 divided by t2 minus t1, or the velocity can be calculated by x3 minus x1, that is x3 minus x1 divided by t3 minus t1, or this velocity can also be calculated at x3 minus x2 divided by t3 minus t2. Okay. Now, this is the equations are used to calculate the velocity, and the velocity, frequency and the wavelength in communication system are related by one particular equation, that is v is equal to f into lambda. V is the velocity with which these particular waves are moving, and f is the frequency of this particular wave, and lambda is the wavelength of this particular wave. Coming to this transmission line equations. Now, before going to this particular transmission line equations, so whatever these particular transmission lines are there, so these transmission lines are considered as a distributed parameters. In a normal circuit theory, whatever the circuit elements are there, for example, inductors are there, the resistors are there, so we are taking those particular elements as a lumped elements. But for the microwaves are considered, so whatever these resistors and inductors are there, so they are taken as a distributed one. That means throughout the length of the particular line, so this inductors and the resistors are present. So therefore, so these parameters in this particular in the micro communication circuit, they are taken as a distributed parameters. And now in the normal circuit theory, so what we are doing is that using the voltage and the current and the Kirchhoff's laws you are applying, and then we are analyzing the circuits. But those particular things are not applicable in this particular microwave lines, because here the microwave signals are transmitting, okay, in the form of electromagnetic signals, that is both electrical energy is present and both the electromagnetic energy is also present. So therefore, so those particular things cannot be directly applicable to this. And second case is that in order to analyze this particular transmission lines, so the two methods have been used. One is the Maxwell equations method, and another one is distributed circuit theory. In the Maxwell equations, we have 3 time variables and 3 space variables are there. Totally 6 variables are there. Whereas in case of the distributed circuit theory, we have 3 time variables and we have only 1 space variable. So the number of variables here has been only 4. So therefore, instead of using the Maxwell's equation for the analysis of the transmission lines, we are going for the distributed circuit theory techniques. Now this is the equivalent figure, okay, of particular transmission lines. Okay. So instead of showing the entire length of the lines, okay, a small length delta z, okay, here in this particular figure, whatever this particular delta z is written or shown, so this delta z is a small length of the line. In order to analyze the circuit, entire length is not taken into considerations, a small length delta z is taken into considerations. Now as usual, so this particular network, just if you recall your memory of your earlier class, so it is nothing but a T type of the circuit. Okay, as you studied there, pi and the T, so it is nothing but a T type of the circuit what you are having here. So here you are applying the voltages and here you are getting the output voltages. And so this particular transmission lines, okay, in the micro communications, consisting of the components, one is a resistor and another one is a inductors. Okay. And these resistors and inductors, and also we have a capacitance and also we have the inductances. The illustration of this particular transmission lines is shown in these particular figures, where the various components, what it has been shown. So in this particular circuit is where R is a series resistance L is series inductance, G is shunt capacitance, G is shunt conductance, C is shunt capacitance, omega into L is series reactance, omega into C is shunt susceptance, and Z is equal to R plus J omega L is called as a series impedance, Y is equal to G plus J omega is called as a shunt admittance, I equal to Vz of t. So, you can also write it as I adjacent e to the power of j omega t, it is a current at any point, V is equal to Vz of t, this is equal to V adjacent into e to the power j omega t is voltage at any point. That is, so these two equations will give you the voltage and the current at any point of the transmission line from starting end to the receiving end, okay, or from the sending point to the receiving point, and this L is called as a length of the lines. Okay, now let us derive an equation for the characteristic impedance of this particular transmission lines. So, for this purpose let us assume the signal is sinusoidal variations. Let us assume that sinusoidal variations, then voltage is given by these particular equations and the current is given by these equations. Then the change in the voltage with respect to the change in the distance, as the signal is transmitting through the transmission lines, okay, the voltage changes as the distance changes. So, that you have to calculate. So, that is change in the voltage with respect to the change in the distance, that is dz, that is change in the voltage delta is equal to Ri into delta z plus L into dou I by dou t into delta z, the change in the voltage is. Now, if you just simplify this particular, that is delta V divided by delta Z, you take this particular term, this delta Z you take it in this particular place. So, then this equation can be simplified to this. Now, in this particular equation, if delta Z tends to 0, okay, so then, so this equation will be delta V divided by delta Z equal to dou V divided by dou Z. Therefore, dou V divided by dou Z is equal to I into R plus L into di by dt, okay, call it as equation number 5. Similarly, as you are calculating the change in the voltage, you can also calculate the change in the current. Change in the current can be calculated from these particular equations, and here also once again, so you can simplify these particular equations, take the delta Z in the denominator term, then it becomes G into V plus C into dou V by dou t. Again, as you did in this particular case, as delta Z tends to 0, so then delta I divided by delta Z it becomes dou I by dou Z, okay. Then dou I by dou Z is equal to GV plus C into dou V by dou t, okay, call it as an equation number 6. We will differentiate this particular equation 5 with respect to Z partially, then the partial differentiation of this particular equations is given by dou square V by dou Z square plus R into dou I by dou t plus L into dou by dou t of dou I by dou t. So, let us call it as equation number 7. Using the equation number 6 and 7, we can write dou square V by dou t square as R into GV plus C into dou V by dou t plus L into d by dt, GV plus C into dV by dt. And these equations, so just if I multiply R with this particular term and this L with this particular term and taking all the terms as a common, so then you can write this dou square V as R into GV into RC plus GL into dou V by dou t plus L and C into dou square V by dou t square. Similar to this, you can write the current also, that is dou square I by dou t square is equal to with the equation number 9. Now, let us denote, so what are the voltage and the current which are flowing through this particular transmission line. V of Z comma t, okay, is equal to V of Z into e to the power of j omega t, and I of Z comma t, you can write it as I of Z into e to the power of j omega t, where V of Z is the voltage, this is the pure voltage which is a function of Z, and I of Z is a current which is a pure function of Z. Now, we have to differentiate the equation number 10 with respect to Z. Okay. So, this equation we have to differentiate with respect to Z. We differentiate with respect to Z, then we are getting the equation number 12, and the same equation number 10 if you differentiate with respect to t, we are going to get this equation, And this equation once again we are differentiating with respect to t. Once again we differentiate with respect to t. So, this equation we are going to get it as this. In this you simplify this, we are going to get as equation number 14. How we are getting it is, here j is there. So, j square is minus, okay, and omega square we are getting, and v of z we are writing it as it is, j omega t we are writing it as it is. So, consider the next parameters, that is the characteristic impedance, and it is given by z0 equal to root of z divided by y, where z is the impedance of the transmission line and y is the admittance of the transmission lines, and we know that z is equal to r plus j omega l and y is equal to g plus j omega c. Substitute in these particular equations and take this particular j omega l outside, then it becomes root of 1 plus r by j omega l. Similarly, j omega c we are taking it outside, then it becomes 1 plus r by j omega c. Now, then this j omega and j omega will get cancelled and you left with l and c, okay. And now we will write it as root of l by c into 1 plus r by j omega l raised to 1 by 2, and similarly 1 plus g by j omega c into raised to 1 by 2. Now, expand this equation using the binomial theorems. When you expand this equation using the binomial theorems, we will get these particular equations. Then once you get this one, multiply these two brackets, okay. So, then we are going to get them, then you are simplifying these equations, okay. When you simplify, so you will get these particular equations. Now, so as you know, the r is very less than omega l and g is less than omega c. If that is the case is there, so then what happens is that, that is in this equation 1 by 2 r by j omega l minus g by j 2 omega c plus rg divided by 4 omega square lc. So, this term, what the term we are having here, so this value is very less than 1. So, then, so this term what it is there, so the value is going to be nearly equal to 0, okay. When the value is nearly equal to 0, then what happens is it is going to be 1 plus 0, that value is equal to 1. Then the root of LC into 1 is going to be root of L by C. So, therefore, the characteristic impedance is given by the root of L by C. Okay, now, so let us consider one more parameters, that is the wavelength. So, the wavelength is calculated by, so 2 pi by beta. So, now lambda is equal to 2 pi. We know that the values of beta is equal to omega into root of L into C. Substitute the values of beta is equal to omega into root of L into C. And we know that omega is equal to 2 pi f. Substitute omega equal to 2 pi f in this equation and keep this LC as it is. Then, so this 2 pi and this 2 pi will get cancels. So, then we left with lambda is equal to 1 by f into root of LC. Then, so let us consider one more parameters. So, that is the velocity of propagation, that is Vp. So, the velocity of propagation is calculated by lambda divided by t. So, this you can write it as lambda into f, because 1 by t is equal to f. Now, so this, to simplify this particular equation further, what we will do, we will write this lambda into f as it is. Then I am dividing and multiplying this particular equation by 2 pi, that is I am multiplying it by 2 pi and dividing it by 2 pi. So, the value of the equation remains same. Now, once we divide and multiply by 2, then readjust these particular terms. If I rewrite these particular terms, so then becomes lambda into 2 pi f divided by 2 pi. Okay, then what you have to do is, so divide this particular equation. Okay, divide this particular equation by lambda. When you divide this particular equation by lambda, okay, then what happens is, so this lambda will go and you are getting 2 pi by lambda here. Okay, now we know that this 2 pi f is equal to omega and 2 pi by lambda equal to b. So, that in this equation we know that 2 pi f is equal to omega, substitute 2 pi f by omega, and 2 pi by lambda is equal to beta. So, substitute as omega by beta. Therefore, Vp is equal to that omega we are writing it as it is. We know that beta is equal to omega into root of Lc. So, substitute in this particular case omega into root of Lc, and this omega will get cancelled. Therefore, that Vp is equal to 1 by root of Lc. These are the some of the equations which are used to calculate the various parameters. Solve some problems on this particular transmission lines. So, the first problem is a microwave generator at 1.2 gigahertz supplies a power to a micro transmission line having the following parameters. Resistance R is given as 0.8 ohms per meter. Conductance is given as 0.8 millimoles per meters, and inductance is given as 0.01 micromole per meters, and capacitance is given as 0.4 picofarad per meters. And you are supposed to calculate propagation constant, attenuation constant, phase constant, and the characteristic impedance. Okay. Now let us solve these particular problems. So the propagation constant is given by the equation gamma is equal to root of z into y, where z is the impedance and y is the admittance. In this, whatever the z is there, so z can be calculated with the help of this equation, that is z is equal to r plus j omega l. Now in the given problem, r value is given and l value is given and omega value is given. That is, omega value can calculate it from this particular frequency 1.2 GHz, because omega is equal to 2 pi f. Substitute all these values, r value is substituted here, then j omega is equal to 2 pi f, that is 2.f is 1.2 into 10 to the power of 9 into L is 0.01 microfarad, what it has been given, into 10 to the power of minus 6. Okay. Now if you simplify these particular equations, we are going to get, now we are going to get, so these particular values. Then calculate the values of y. So y is equal to, so g plus j omega c, substitute the values of g what it has been given in the problem, plus j omega is equal to 2 pi f into c value is given. If you simplify this particular equation, I am going to get the values of y is equal to, so these values. Now as you know, the gamma is equal to root of z into y. Here we calculated the values of the z and here we calculate the values of the y. Substitute the values of z and y in this particular equations, and if you simplify it, so I am going to get the value as, so this. Okay. So that is, also we know that gamma is equal to alpha plus j beta. Okay. So then alpha plus j beta, if you can write it as, that is 0.0654 plus j 0.48. Okay, once again I am repeating. So gamma is equal to root of z into y. So z you have calculated from these particular equations and y you have calculated from these particular equations. Substitute the values of z and y in this particular equation, and if you simplify it, you will get the values as, so this one. And now we know that gamma is equal to alpha plus j beta. Okay. Now when the gamma is equal to alpha plus j beta, if you write, so this is value we are getting, that is equal to 0.654 plus j 0.48. Value of gamma is equal to alpha plus j beta, so that is 0.0654 plus j 0.48. So this is the value we already calculated, and from this particular values, so you can calculate the another two parameters. One is attenuation constant, another one is the phase constant. In this, so whatever this particular 0.0654, so it is nothing but the alpha, and what is its 0.048 is there, it is nothing but the beta. Therefore, our attenuation constant is equal to 0.0654 Nepers per meter, and the phase constant beta is equal to 0.48 radians per meter. Then we will calculate the characteristic impedance. The characteristic impedance is calculated by the formula, that is root of z divided by y, and already we calculated the values of the z and already we calculated the values of the y. Substitute the values of the z and substitute the values of the z, simplify these particular equations. So we are going to get it as 155.83 at an angle of 7.16. Once you substitute the values and you simplify these particular equations, I am going to get the values of Z0. So this Z0 is the characteristic impedance of the transmission line. So let us consider one more problem. In a certain transmission let us consider one more problem. In a certain macro transmission line, the characteristic impedance measured to be 210 at an angle of 10 degrees and the propagation constant is 0.2 at an angle of 78 degrees. Determine the primary constant of the line if the frequency of operation is 1 GHz. What the problem is given is that here the characteristic impedance is given and the propagation constant is given and the operating frequency is given, and it is asked to determine the primary constant of the transmission lines. So, the primary constant of the transmission lines are nothing but your resistance and your inductance and your capacitance. So, these three parameters you are supposed to calculate. That is solution. Given values is Z0 is given, gamma is given and F is given. Now, we know that R plus j omega L is equal to gamma into Z0. Now, gamma into Z0, gamma is given in this and Z0 is given, substitute the values and simplify this part. Then we are going to get this equation as 1.466 plus j 41.97. Then equate this term, a real terms and a imaginary terms. Equating the real term is this one. This real term is nothing but your R values, and the imaginary term, now equating the imaginary terms. Now, the imaginary terms what you are having here is 41.97, that is omega L equal to, omega L is nothing but 2 pi F L, this is equal to 41.97, and therefore, in this equation L equal to 41.97 divided by 2 pi F. F value you know that 1 gigahertz has been given in the problem, that is 1 into 10 to the power of 9. So, if you simplify this equation, we are going to get the values as 6.68 millihenry per meter. This is the value of the inductance. Next, also you know that G plus j omega c is equal to gamma divided by Z0, and here you know the values of the gamma and here you know the values of the Z0, substitute the values and just simplify this. So, we are going to get this particular values. Once you get these particular values, once again equate the real terms and also equate the imaginary terms. So, this is my real term and this is my imaginary term. Okay. The real term is going to give the values of the G is equal to 3.5677 10 to the power of minus 4 mho per meters, and the imaginary terms WC is equal to 8.83 into 10 to the power of minus 4. From this, C is equal to this term divided by omega is equal to 2 pi F, F is the values 1 into 10 to the power of 9. If you substitute the values and simplify it, so we are going to get the values as, so this, that is 0.14 picofarad per meters. So, therefore, so C you have calculated, G you have calculated and L you have calculated, okay, and R value you have calculated. So, therefore, so this R, L, C and G are the primary constants. So, let us consider the input impedance of a transmission lines. Okay, for this particular purposes, let us consider this particular circuit, a transmission line, and this is the input side and this is the output side. Okay. Now, the output is terminated with the load impedance ZL, and the input is connected with a generator. A voltage is represented by Vg and Zg is the generator impedance. Here whatever the Zg is there, it is a generator impedance, and whatever the Vg is there, it is the generator voltages. And the voltage measured, okay, with at a certain distance from the transmitting end or the sending end, it is represented by V plus, and the voltage measured with a certain distance from this particular receiving end, okay, at the load end is represented as V minus. Okay. And so, whatever the voltage you are measuring across this particular load, it is represented by VL. Okay. And now, this particular figure is a microwave transmission line of a length L terminated in ZL. That means to say that instead of considering the entire length of the line, a small line is taken whose length is equal to L, and this line is terminated with a load impedance ZL. Now, so let us consider the voltage and the current across these transmission lines to calculate the input impedance. So, the voltage is calculated by V of Z is equal to VL cos H of gamma Z plus IL into Z naught into sin H of gamma into Z, and current is given by I of Z is equal to IL cos H of gamma into Z plus VL divided Z naught into sin H of gamma into Z. call it as equation number 1 and call it as equation number 2. Then we are supposed to calculate the input impedance, that is the input impedance of a transmission line of the length L. The input impedance is given by Z is equal to V of Z divided by I of Z. So here you are having a V of Z and here you are having a I of Z. Substitute the values of V of Z here and substitute the value of I of Z here. Okay. Once you substitute it here, now from this particular figure, okay, I have to measure this particular voltage. So the voltage at the load is VL. So what is this particular VL is equal to IL into ZL. So that is the amount of the current what it is flowing through this particular load is IL. IL into ZL is going to give us the voltage VL. That is VL is equal to IL into ZL. Now substitute this VL because in this equation you are having the VL term. Substitute this value. So in this particular equation, that is VL equal to IL into ZL. Once you substitute this, we are going to get this equation. Now from this particular equation, here you are having IL and here you are having IL and IL. Take this particular IL term common and then numerator you are having the IL and denominator IL and IL will get cancelled. You left with this particular term, that is Zs is equal to Z0 into ZL cos h of gamma L plus Z0 sin h of gamma L divided by Z0 cos h of gamma L plus ZL sin h of gamma L. Let us consider one particular problem on this input impedance. So the problem is the characteristic impedance of a certain line is 710 at an angle of 14 degrees and the propagation constant is given as 0.007 plus j.028 per kilometer. The line is terminated in 300 ohm resistors. Calculate the input impedance of the line if its length is 100 kilometers. For the solution is considered. So write down what are the given parameters are there. Z0 is given, gamma is given, ZR is given and the length is given. And you are supposed to calculate this particular Zs at a length of 100 kilometers. And we know the formula for this particular Zs. Zs is equal to Z0 into ZR cos h of gamma L plus Z0 sin h of gamma L. So divided by Z0 cos h of gamma L plus ZR sin h of gamma L. And to calculate these values, first let us consider this cos h of gamma L values. Cos h of gamma, we know that gamma is equal to alpha plus j beta. So in place of this gamma, substitute the values is equal to alpha plus j beta into L. Okay. Then we simplify this particular equations, we are going to get a cos h of alpha L plus j into beta L. Now here, substitute the values of this alpha and the beta values. So then if you simplify it, I am going to get the values as cos h of 0.7 plus j 0.28. Then from the geometry, we know that cos h of a plus j beta is equal to cos h of a into cos h of b plus sin h of a into sin b, and sin h of a plus j beta is equal to sin h of a plus into cos of b plus j cos h of a into sin b. Okay. Now therefore cos h of gamma L is equal to cos h of 0.7 plus j 2.8. So let us, because this particular equation we are writing in this particular form, cos h of 0.7 into cos h of 2.8 into 180 degree divided by pi plus j sin of h of 0.7 into sin of 2.8 into 180 degree divided by pi. If you simplify this equation, I am going to get the values of cos h of gamma L. So this cos h of gamma L is these values. Next is what you are supposed to do is, so we are supposed to calculate the values of sin h of gamma L. Once you get the sin h of gamma L and you substitute the values in this particular equation, then we are going to get the Zs values. Okay. Now for this particular purpose, now let us calculate the values of sin h of gamma L. Now sin h of gamma L equal to sin h of 0.7 plus j 2.8. Simplify this particular equation. You are writing this equation in the form of sin of a plus b formulas, sin and cos and the sin form. Now the sin h of gamma L equal to, we are going to get it is after simplification, we are going to get it as 0.715 plus j 0.446. And for us, okay. Now, so let us calculate the values of sin h of gamma L. Okay. Now, sin h of gamma L equal to sin of 0.7 plus z 2.8. Now, you substitute these values in the trigonometric identity forms. So, then we are going to get this value as 0.715 plus j 0.446. And in the given problem, ZR value is given and Z0 value is given, and substitute these values, all these values, that is ZR, Z0, sin h of gamma L and cos h gamma L in the equations. So, when you substitute it, Zs equal to, so these are the terms what we are getting, that is sin values and the cos values, ZR values and Z0 values after substitutions. Then once if you simplify these particular values, going to get, so these particular equations. Okay. Further simplification of this, we are going to get it as this. Once again, if you simplify this, I am going to get it as this. Once again simplify, we are going to get it as 632.4 at an angle of 3.87 degrees. And so this is the impedance of the transmission lines, which has been asked at a distance of 100 kilometers.